Okay, welcome back. All right, well, if you remember last time we were talking about ions, and we said that the driving force behind ions forming, at least the ones with noble gas structures, is to try to get that 2, 10, 18, 36, 54, 86 electrons, the same number of electrons as that the noble gases, because those are the magic numbers. That just makes an atom incredibly stable. The driving force behind your polyatomic ions having the charges they have is actually really similar. We'll talk about it when we start talking about Lewis dot structures and theories of covalent bonding and all sorts of stuff like that. But that's kind of the driving force. All right. If you'll remember, the downside to gaining or losing electrons is you're not electrically neutral anymore, and so you're violating the principle of neutrality. The upside is you got that nice noble gas structure. And so it's kind of a give or take type thing here. It's, you got an advantage and a disadvantage. So if you can manage to not violate the principle of neutrality too badly and still get that noble gas structure, then I guess that's a good thing. So I guess everything in life's a trade-off, right? Well, wouldn't it be nice if there was some way I could kind of have my cake and eat it too? If there was some way I could have that nice noble gas structure, but I didn't have to worry about the principle of neutrality thing. Well, how could I ever possibly do that? Well, that brings us to what we need to talk about today. All right, and these are writing formulas for ionic compounds here. All right, now, when you write the formula for an ionic compound, what you do is you simply apply the principle of neutrality. All right, I'm going to go through this. I'm going to explain this. Students have issues with this. If you're going to mess something up in chapter 2, it's probably going to be what we're going to talk about next. They just don't get it. It seems really simple to me, but yeah, I've been doing it a while, I guess. And I don't seem to have a problem understanding it, but for some reason people just have a problem with this. So maybe it's just the way I explain it. I don't know. Okay, you can leave comments maybe in the Canvas section there if you don't get what I'm trying to say. So if you don't understand this the first time, then you're not the only person who's ever had problems with it. So fight your way through it as best you can. All right, but I'm going to try my best to explain it as simply as possible. Okay, so let's say for example, I have calcium fluoride. What is the formula for calcium fluoride? Well, first thing you do is you say, okay, well, what type of ion does calcium form? Well, I look in the periodic table. The periodic table is your friend. The periodic table will tell you a lot if you know what to look for. By the way, you'll have a periodic table on every test that you take. I'll probably put one up there. You can download and print it there. But yeah, you'll need a periodic table. And so I look for calcium in the periodic table, and I see it's in group 2. So what does that mean? Well, that means when calcium forms ions, it forms +2 ions, because remember, all the elements in group 2 form +2 ions. Okay? All right, well, let's see here. I got fluorine. What type of ion does fluorine form? Well, I look in the periodic table. I see fluorine is a halogen. It's in group 17. And so I know all of those form -1 ions. Okay? So now the question becomes, what's the smallest number of calciums and fluorines I can put together and get something to add up to 0? All right, if my calciums are +2 and my fluorines are -1. Well, if I take 1 calcium at +2 and I take 2 fluorides here at -1, my calcium's +2, my 2 fluorides together add up to be what? -2? What's +2 and -2? It's 0. See, all you got to be able to do is count to 0. If you can count to 0, you can write formulas for ionic compounds. All right, and so the formula for calcium fluoride is CaF2. All right, now the charges aren't written here. Okay, I think that confuses people, but they're still there. Notice the whole thing is neutral. If you write the formula for an ionic compound and it doesn't add up to 0, you have done it wrong. Start again. When you see this, what does that mean? Well, that means I've got a calcium 2+, and I've got these 2 fluorides here, and they're bonded together somehow. Is this the exact crystal structure? No, but they're bonded together. What keeps them together? Well, the fact that they're opposite charges, see? And so that's what kind of keeps them together. And that's an ionic bond. Okay? And so this is calcium fluoride, Ca(L2). When you see this ought to pop into your head. If I drew this, and of course you knew what the atoms were, you should be able to write me the formula here. Got it? Can you visualize? Okay? Let's try another one. Strontium phosphide. Strontium. Where's strontium in the periodic table? Well, it's also in group 2. So what type of ion does that form? Well, that forms +2. What's a phosphide? Well, a phosphide is a phosphorus monatomic ion. It's not a PO4. What's a PO4? What's a phosphate? It's one of your polyatomic ions you're supposed to know. So you got to know your polyatomic ions. Okay, but this is a phosphide. Remember, "ide" usually means the monatomic ion. All right, so what charge do you think phosphorus would form? Well, look in your periodic table. It's sitting there in group 15. So it looks like it needs to gain 3 electrons to have a nice noble gas structure. So it's going to form a -3 ion. So now the question becomes, what's the smallest number of little strontiums, 2 pluses, and little phosphides, 3 minuses, I can put together and get something that adds up to 0? Well, I can't take 2 of these and 1 of those because that doesn't add up to 0. So the smallest number that I can put together would be maybe, what, 3 of these? If I have 3 strontiums, what's my charge? Well, that's +6. 2 phosphides gives me a total charge of what? -6. So +6 and -6 equals 0. So therefore, the formula for strontium phosphide is Sr3P2. Notice everything adds up to 0. Charges are still there, you just don't show them in the formula. When you see this represents something like this. See, here's my 3 strontiums at +2. Here's my 2 phosphides here at -3. Is this the exact crystal structure? No, it's not. But all these ions are kind of held together by opposite charges. The fact that opposite charges attract. Let's try one more. Aluminum nitrate. So what type of ion does aluminum form? Well, from our rules last time we talked about is +3. Okay, what is a nitrate anyway? Well, a nitrate is an NO3. What charge does nitrate have? -1. How do you know this? Because you memorized it, because I told you to in the last video. See, if you don't know your polyatomic ions, you're going to have a really hard time writing formulas for ionic compounds. Got to know those polyatomic ions. So commit those to memory. You know, I don't ask you to memorize a lot in here. You can't memorize everything. But there are some things that are important to have in your head, working knowledge. And this is one of those things. So commit them to memory if you can. All right? So I've got a nitrate here with a -1. So what's the smallest number of aluminums and nitrates I can put together and get something that adds up to 0? Well, 1 aluminum at +3, and then 3 nitrates at -1. 1 aluminum here +3, 3 nitrates -3, +3 -3, 0. So the formula would be AlN3O9, right? Well, no, can't write it that way. Okay, because that says an aluminum attached to some sort of N3O9 molecule or something like that, and that's not what we have here. Maybe I could write like Al3NO3. Well, that doesn't mean anything. You can't put coefficients in the middle of a formula. All right, so how would I write this to say 1 aluminum and 3 nitrates? Well, I write an Al, and then in parentheses, I put my NO3, and then I put a subscript down here, 3. What this means is I have 1 aluminum, and I have 3 nitrates. Each nitrate contains a nitrogen and 3 oxygens. Schematically, it would look like this. Here's my aluminum 3+. I have 1, 2, 3 nitrates. That's what this is. And each of my nitrates contains a nitrogen and 3 oxygens. They stay together as a unit. And that's how you write the formula for aluminum nitrate. Here is a trick. It's a trick. It works, but it's a trick. But, you know, maybe it's a way you could check yourself. I prefer that you do it the other way because you actually understand what's going on. You know, knowing how to do something and knowing why it works is always better than just knowing how to do something. You always remember the things. It's like, oh yeah, well that makes sense. That's why we do it that way. If you just memorize a rule, it's kind of, you know, goes in one ear and kind of out the other, and you forget about it. All right. So here, this is called a crisscross method, and it, like I say, it's a trick, but I guess it does work. So what you can do is you can ignore the numbers here, the plus and minus here, and then you just take this number and you put it down here. You take that number and you put it there, kind of like an X. So the formula is CaF2. See? Here I can take this 2, put it down here, take this 3 and put it down here, Sr3P2. Al1NO3 3. See? Works. Okay. Now, do you ever get yourself in trouble with that? Well, yeah. Let's say you had something like calcium oxide. Calcium is +2. Oxygen forms a -2 ion. So if I try the crisscross method, I'll get Ca2O2. Is that the actual formula for calcium oxide? Well, no. The formula for calcium oxide is just CaO, because you need 1 + 2 and over here 1 + 2. And you need 1 - 2 to come together, and that's the smallest number of ions you can put together and get something that adds up to 0. Okay, is it a fatal mistake? Well, no. If you get Ca2O2 or something like that, if you get something that's reducible, just reduce it down. You know, 2 to 2 reduces down to what? Well, 1 to 1. All right, so I can't say no, don't use that method because it gives you horribly wrong answers. You know, you can fix it. So, you know, if that's what you got to do, that's what you got to do. I really prefer the smallest number of ions thing because that's actually what's actually going on. But you could always check your work, I guess, the other way if you wanted to. Okay? Why do calcium ions and fluorine ions come together? You know, and why do they come together in a 2-to-1 ratio here? Well, remember we talked about our ions and our noble gas structure and our principle of neutrality. Okay? Notice that each of these ions has that nice noble gas structure. What's the problem? Well, it's got a charge, right? So can I bring you a jar of fluoride? No, because solids, liquids, low temperature gases have to be electrically neutral. Can I bring you a jar of calcium fluoride? I sure can, because notice that each of these ions has a noble gas structure, but when you look at the whole thing, what's the total charge? It's 0. It's neutral. So ionic bonding occurs here. So I can kind of have my cake and eat it too. Each of these little ions here has a nice noble gas structure, but at the same time, the whole thing is neutral. And so, yeah, I can bring you a jar of strontium phosphide. I can bring you a jar of aluminum nitrate. I can't bring you a jar of nitrate, but if I put it with cations and make something neutral, yeah, I can bring you a salt that has nitrate in it, like aluminum nitrate or sodium nitrate or something like that. So that's the reason why ionic compounds form. It's a way to have that, one of the reasons. It's a way to have a nice noble gas structure in many cases and also be electrically neutral at the same time. Look, this is the reason compounds form, period. You know, if every atom had a nice stable structure and was happy the way it was, what you'd see is you'd see 91, 92, about 92 naturally occurring elements there, about 92 naturally occurring elements just floating around the universe. They wouldn't bond. The reason they bond is because they're happier together than they are apart. It's the reason people get married, right? You know, if you're going to get married, why would you get married if you're happy being single? I mean, that would be kind of silly, right? You get married because you think there's a possibility that you're going to be happier with that other person than if you went your separate ways. Hopefully it works out for you. All right, but that's chemical bonding. That's chemistry. Now, again, if all this didn't happen, I wouldn't have a job. In fact, you know, you wouldn't be in this class. You wouldn't be here, period, because you're made up of some very complex chemicals. The universe would just be a kind of a free-floating soup of elements, and that's it. So, yeah, something to think about there. Late at night, if you happen to be reading this, watching this late at night, I don't know. All right. But that's why things have to be electrically neutral here. Okay? All right, so if I gave you a name, you could write me the formula. All right, so now the question is, can we play the game the other way around? Can you play it backwards? What if I gave you a formula? Could you give me the name? All right, so how do we do that? Well, that leads us into our next section, which is naming compounds. So let's talk about naming compounds. How you name compounds depends on what type of compound it is. All right, if it's an ionic compound, it has a certain nomenclature or way you name it. So how does that work? Well, in an ionic compound, what you do is you name the cation first. Remember, the cation is the positively charged ion. And then you name the first part of the anion, and then you slap an "ide" on the end of it. Okay? If it's a polyatomic ion, you don't have to put the "ide" on the end of it. You just say cation and then the anion. All right. This is the reason why if it's a monatomic ion, usually they end in "ide." This is the reason why, is because of this naming thing here. So oxygen becomes oxide, sulfur becomes sulfide, chlorine becomes chloride, bromine becomes bromide, carbon becomes carbide, iodine becomes iodide. See, just take off the ending, slap on an "ide," there you go. And that's it. Okay, so time to play, name that compound. So CaBr2, name that compound. Well, my cation is what? Calcium. My bromine here, take off the ending, put on an "ide," so this becomes calcium bromide. And that's it. Now, if you called this calcium dibromide, would that be wrong? That would be wrong. It's calcium bromide. But how do you know there's two bromines there if you just say calcium bromide? Well, you know calcium always forms +2, and you know that bromine always forms -1. So the only possible formula for calcium bromide would be CaBr2. So you just say calcium bromide. You assume that your reader knows a little something about chemistry. All right, what about Na2SO4? What would you name that? Well, my cation is sodium. What's an SO4? That's a sulfate. So this is sodium sulfate. All right, did you sit there trying to name this as some sort of sodium sulfur oxide compound? No, it's sodium sulfate. These go together as a unit. This is an SO4. It's got a -2 charge, and it's called a sulfate. See, if you don't know your polyatomic ions, you're going to miss that. You've got to be able to recognize those polyatomic ions when you see them. And it's just sodium sulfate. It's not disodium sulfate. It's not sodium disulfate. It's not sodium 2 sulfate. It's sodium sulfate. It's really that simple. All right, well, let's say, for example, I had something like iron oxide. What's the formula for iron oxide? Well, FeO is iron oxide, but there's also an Fe2O3, and that's iron oxide as well. Do both of those exist? Yeah, they actually both exist. So if I say iron oxide, for example, and I say, hey, hand me that bottle of iron oxide, which bottle do I want? Do I want the FeO or do I want the Fe2O3? Don't know, right? So what we've got now is we've got one name for two compounds. Is that a good thing? Well, no, that's not a good thing. We want one name for one compound, one name. That's what we're looking for. That keeps things from getting confused. So what's the problem here? Why do I have two different iron oxides but I only have one calcium bromide? Well, iron is a transition metal. All right, and what do we know about transition metals? Well, they always form cations, positively charged ions, number one, and also they can form multiple types of ions, and that's what's going on there with my iron oxide example. The one way that you deal with this, the old way we used to do it, is the one that's in the lower oxidation state. In other words, the lower charge was the Us, and the one with the higher oxidation state is the Ik. So FeO was ferrous oxide, Fe2O3 was ferric oxide, and that got us along pretty far. But what do you do when you have things like manganese with like 4 or 5 different oxidation states? Now I've got to come up with some sort of a prefix, and one for higher than that, and then one for higher than that, and one in the middle, and it can get really confusing. It's kind of almost like the hypoiite 8 per 8 thing there. Yeah, we don't want to do that. All right. So what do I do if I've got a transition metal? Well, if you have a transition metal, and of course that includes groups 3 through 12, and also the ones down at the bottom, and also the ones below that stair step in the periodic table. We said for our intents and purposes, we're going to call those transition metals. The way you name them is you name the cation, and then you put a Roman numeral indicating the charge in the middle, and then you name the anion. So it's one extra step. So for example, here is SnBr4. Name that compound. Well, Sn is 10. Okay, Br is bromine. So take off the ending, slap on an I. So this is 10 bromide. But since it's a transition metal, I have to put the charge on the 10 in there. All right, so remember I said that there would come a time when I could give you a formula and you could tell me the charge on it? Well, that is today. So here we go. I know that bromine forms what type of ion? -1, right? Group 17. Okay, so I got 4 of those for a total what? -4. If these add up to be -4 over here, what does this 10 have to be? It has to be +4. Do you see that? Because +4 minus 4 equals 0. Again, it's got to add up to 0 in a formula. So the way I write the name is this is 10 parentheses Roman numeral 4, bromide. I don't have to put the plus because it's always positive. Transition metals always form cations. I can just write the 4. What about this one? Here is cobalt, and I got an SO3. What's an SO3 polyatomic ion? Well, that's a sulfite. Okay, remember SO42 minus is a sulfate. 1 less oxygen than the 8 is the ide. What's the charge on a sulfite? -2. Because remember, 1 less oxygen than the 8, same charge. So an SO3 2- is called a sulfite. If this has a -2 charge, what does this cobalt have to be? Well, it's got to be +2. See, because +2 and -2 equals 0. So the way I would name this is this would be cobalt 2 sulfite. Make sense? Why did I call this calcium bromide? Why didn't I call that calcium 2 bromide? By the way, would it be wrong if I called that calcium 2 bromide? Yes, it would. This is just calcium bromide. Well, why? Well, because calcium always forms +2. All those elements in group 2 always form +2 ions. So I don't have to put the 2 there. It's redundant. It's just calcium bromide. But the transition metals can form multiple types of ions, and that's why you have to put the Roman numeral. All right? So 2 different types of compounds. Elements in group 1 and 2, and 5, nitrogen, I guess, really. Well, it doesn't really matter. It's just really the metal. Groups 1 and 2, and a couple of exceptions here. We'll talk about that. Aluminum, groups 1 and 2 in aluminum, and no Roman numeral. If it's a transition metal, then you use a Roman numeral. Okay, now are there exceptions to the rule? There's always exceptions to the rule. All right, so here are the exceptions to the rule. Aluminum, always forms +3, so no Roman numeral. Okay, the ammonium cation, that NH4 with the +1 charge, that's always +1. And so that's an ionic compound. You don't put the Roman numeral after NH4+, or NH4, the ammonium cation. All right. There are a couple of transition metals that only form one oxidation state. And these are kind of exceptions to the rule. One of those exceptions to the rule is zinc. Zinc always forms +2. So usually you just say like zinc sulfate, zinc carbonate. You don't put a zinc 2 there. All right. Underneath zinc is cadmium. Cadmium pretty much always forms +2. So you don't usually use a Roman numeral with that one. Okay. Silver Silver pretty much always forms +1, so you can just say silver sulfate or silver chloride. You don't have to say silver 1. All right, and so those elements right there that kind of make a little backwards L there in the periodic table, you normally don't use a Roman numeral. Scandium pretty much always +3, and we can play that game. We can play exceptions to exceptions to exceptions to the rule, in here all day. Let's just not do that. So what it comes down to is if you put a Roman numeral after zinc or cadmium or silver, I probably won't count off, but technically they don't use the Roman numeral. All the rest of your transition metals, we'll say it that way, use your Roman numeral. All right? No Roman numeral for group 1, group 2, NH4 plus, or aluminum. Okay? And if you can do that, you're great. If you know that zinc and cadmium and silver don't use a Roman numeral, then you're even better. You're extra special awesome. So do the best you can. All right? But yeah, that's probably good enough. Okay? All right, well, what about, let's say, for example, let's look at this little compound down here. You got this P4O10. Okay? How would I name this compound? Well, I guess this would be what? Phosphorus oxide, right? Well, it turns out there's a P2O5. There's other phosphorus oxides out there as well. So which one do I mean when I say phosphorus oxide? I got another problem here. Maybe I can use a Roman numeral again. Well, the other problem is, what type of ion does phosphorus form in an ionic compound? Well, -3. What about oxygen? Well, -2. Would you expect those phosphorus and those oxygens to come together? Why not? Well, I know that opposite charges attract, but like charges repel. So I wouldn't expect these atoms to come together because they're both negatively charged. They ought to repel each other. But yet they do. So what's going on? Well, what's going on here is you have a different type of bonding other than ionic bonding. These are called covalent molecules. And covalent molecules have covalent bonding, and in covalent bonding, you're sharing electrons. The driving force behind sharing electrons or forming the ions is actually pretty much the same, and we'll talk about it later. But the type of bonding is different here. So I don't have a cation, I don't have an anion. So I can't really use the nomenclature system I've been using before. So what am I going to do? Well, these are called binary molecular compounds, where you have two different types of atoms here, binary. And these are the simplest type of compounds. There are organic compounds which contain carbon. They have their own special nomenclature system, which you're not responsible for. And there are some others out there. But we're going to stick with the simplest ones here. And in binary molecular compounds, what you do is you use Greek prefixes. All right, so for those of you a little rusty on your Greek, let's go over the Greek prefixes here. So if I just say carbon, say for example, I'm assuming that there's one there. It's assumed to mean one. But if I really, really, really want to say, hey, I really mean there's only one of these, I use the prefix mono. If I want to say there's two of something, I use the prefix di. If I want to say there's three of something, tri. Triangle, three sides, three angles. 4 is tetra. Tetrahedron is a little pyramid with a triangular base and 3 triangular faces. Okay, you ever play Dungeons and Dragons, that little 4-sided die? I know you do out there. I see you smiling, so I won't ask you to raise your hand or anything. Nerd. Penta. Penta is 5. Pentagon, 5-sided figure. All right. Hexa, 6. Hexagon. Okay. 7 is hepta. 8 is octa. An octagon, like a stop sign, or if you're into the UFC fighting thing, a ring. 9 is nona. And 10 is deca. What's a decade? Well, that's 10 years. All right. Are there more? Of course there's more. If you can make it up to 10, you're probably going to be okay. All right? Okay. Well, the way this works is pretty simple. You use a prefix to say how many of the first element, plus Prefix for the second element, take off the ending, slap on an "-ide" again. Why, I don't know. That I didn't write the rules, I just report them. So, name that compound. I've got CCl4. Well, that's a carbon. That's a chlorine. How many chlorines do I have? Well, I have 4. So this is carbon tetrachloride. Okay, P4O10. How many phosphorus atoms? Phosphori? How many phosphorus atoms do I have here? Well, I have 4. How many oxygens do I have? Well, I have 10. So this is tetraphosphorus decaoxide. Now, what they'll do is they'll let you play a little fast and loose with the spelling here. They'll let you call this decoxide. They'll let you drop a vowel here because it's just easier to say. So if you call that decoxide, I probably wouldn't take off. I'm just going to go ahead and write them out. So if you write it this way, I'm not going to take that off either. Decaoxide. 4 of these, 10 of these. See, this is actually easier than that stuff up there. See, this just gets easier as we go, doesn't it? All right, what about SF6? Well, that's sulfur. What's 6? Hexa. So this is sulfur hexafluoride. And that's how you name that compound. Make sense? All right. Look, you've been doing this all along, just didn't realize it. What's CO2? Well, that's carbon dioxide. So what's CO? Well, that's carbon monoxide. Poisonous stuff there. But that's carbon monoxide. So yeah, you've been doing this all along. All right. So what's H2O? Well, that would be what? Dihydrogen monoxide or dihydrogen oxide? Well, no, it's just water. All right. Why is it just water? Well, here's kind of the thing. Hydrogen-containing compounds sometimes just have common names. And so H2O is just water. All right. No one calls this dihydrogen monoxide. Okay, it's just water. All right. So sometimes, the reason I'm telling you this is sometimes when you're doing your homework, you'll be sitting there bebopping along, and you get to a compound like N2H4. You think, well, that's dinitrogen tetrahydride or something like that. And you look in the back of the book, and the answer is hydrazine. Or you get to like C3H8. Well, that's tricarbon octahydride. No, that's propane. Where did that come from? Well, hydrazine's a common name. It's just the way it is. Propane is an organic nomenclature system. That's an organic molecule. So different system. All right. So, hydrogen compounds have common names. Do I expect you to know walking in the room that N2H4 is hydrazine? No, I don't expect you to know that. If you call that dinitrogen octahydride, would I count it wrong? I wouldn't count it wrong, although technically I guess it's hydrazine. If you called it dinitrogen tetrahydroxide, would I count it wrong? Yes, because a hydroxide is an OH minus polyatomic ion, not an H. An H would be a hydride. So yeah, I would count that wrong. I do have my limits. But no, I don't expect you to just pull common names out of thin air. But yeah, just be aware if you see something that doesn't make any sense at all, that's probably what's going on there. Okay? All right. Well, what if I took this compound right here, this SN-BR4, and I called that 10-tetrabromide? Would that be wrong? Yes, that would be wrong. This is an ionic compound. This is not a covalent compound. Ionic compounds have their own nomenclature system. Covalent molecules have their own nomenclature system. Do not get them mixed up. What if I called this 10-bromide? Would that be wrong? Yes, that would be wrong because it's 10-4-bromide. All right? Because Roman numeral indicating the charge, that's a transition metal. What if I called this sodium 1 sulfate? Would that be wrong? Yes, it would. It's sodium sulfate. Group 1, you don't use the Roman numeral. They're always +1. What if I called this disodium sulfate? Would that be wrong? Yes, that would be wrong. It's not a covalent molecule. It's just sodium sulfate. Ionic compounds, you don't use the prefixes. So the key is, do not name covalent molecules by the ionic rule system or ionic compounds by the covalent system. They each have their own naming system. Don't get them mixed up. Students will learn one system and they'll try to apply it to everything, but that's not the way it works. Okay? So you may have a question at this point, which I guess you probably should. How do I know if it's an ionic compound or if it's a covalent compound? Because, if I don't know if it's ionic or covalent compound, I'm not going to know how to name this thing. So how do I deal with it? Well, it turns out there's a very simple way. Okay? If you see a metal, and remember the metals are all those elements down below the stair step over to the left in the periodic table. If you see a metal or you see NH4 plus in there, if you see that ammonium cation plus a nonmetal or polyatomic ion, it's ionic, cation, anion. Okay? If you see two nonmetals together, it's covalent. Use the prefixes. And that's how it works. All right? So what I have done for you is I actually have created a nice little chart for you, a little handout chart, a little flow chart for you to look at when you're naming compounds. What will happen is after you use a flow chart enough, you won't need it anymore. All right? It'll be in your head. It'll be imprinted in your head back there. But, if it's not imprinted in your head yet, it's kind of nice to have. So download that, and it looks a little something like this. Very similar to this. Quite similar to this. Okay? And so here's how you name compounds. So it's a little decision tree. All right? So the first thing you have to decide is it ionic or is it covalent? All right, let's say it's covalent. Well, prefix plus first element, prefix plus second element, slap on an ide. All right. What if it's ionic? Well, if it's ionic, now you have if you see a metal or an H4 plus, now you have another decision to make. Is it a group 1, a group 2, aluminum, NH4 plus, zinc, cadmium, silver, or vanadium? Vanadium usually is like, I think, in my periodic table would be +4 or something like that. But yeah, you're probably not going to see that one. But these other three are pretty common here. Is it one of these that is always one particular ion? If it is, cation, anion. All right. If it's a transition metal, then it's cation, Roman numeral indicating the charge, anion. So it's actually kind of 3 different systems here instead of just one. But if you follow the flow chart, you should be able to name anything we throw at you. Okay? Well, let's try. ICl3. Okay? Don't look at the name. ICl3. So ICl3, is it ionic or covalent? Well, it's covalent because they have 2 nonmetals, right? Okay, so how do I name a compound with 2 nonmetals? Prefix, prefix, ide. All right, so ICl3 would be iodine trichloride. Tri means 3. Iodine trichloride. Okay, K3PO4. K3PO4. Okay, is it ionic or covalent? Well, I know it's ionic because I've got that potassium in there, and I know that's a metal. Okay, I've also got that PO4. What's a PO4? That's a phosphate. What charge? -3. Look at your chart. Okay, so yeah, it's got a polyatomic ion in it, so I guess probably ionic, right? But key in on the potassium there. Okay, so now I've got to make another decision. Is potassium a transition metal, or is it one of these that always forms one charge? Well, potassium in the periodic table is in group 1, so it's always +1. So how do I name these? Well, it's just cation, anion. So therefore, I would name this potassium phosphate. See, polyatomic ion here, phosphate. No Roman numeral. Potassium phosphate. No prefix either, just potassium phosphate. Okay, how about Fe2S3? How would I name that? Well, is it ionic or covalent? Well, it's ionic because I've got iron in there, so that's certainly a metal. Okay, is it a transition metal or is it one of these over here? What's a transition metal? So how do I name that? Well, cation, Roman numeral indicating the charge, and then anion. All right, so we go back over here. I know that sulfur forms what? -2. So I've got 3 of those. Okay. So 3 times -2 is what? -6. Okay, whatever these irons are over here, they have to add up to what? +6. Because remember, the sum of the ions in an ionic compound always add up to 0. That's the key. They always add up to 0. So if these add up to be -6, these have to add up to be +6. All right, but I got 2 of them. So if I have 2 of them, they have to be +6. Each of the irons must be +3. So this is iron 3 sulfide. Not sulfate, sulfide, because that's the monatomic there. See, hide. Don't get those mixed up. People get those mixed up all the time. This is iron 3 sulfide. It's not iron 6 sulfide. It's not the total sum charge of all these things over here. It's what each individual atom is, each iron. And each iron is +3, so it's iron 3 sulfide. And that's how you name compounds. So follow the flow chart. Again, people mess this up because they learn one method and they just it's like a guy with a hammer. To a guy with a hammer, everything's a nail. They'll just go through it. They'll just name it that one way. It's just not quite that simple. There's technically three ways, and so you have to figure out what type of compound it is first, so you can name it properly. Okay, follow the flow chart. After a while, like I say, it will get in your head, and you'll be fine. All right. Okay, last thing we want to talk about. I know we're running kind of late here, but hey, let's just finish this whole thing off. Why not? Let's talk a little bit about acids. So what is an acid anyway? We're going to talk more about acids in a later chapter. We're going to talk about acids in excruciating detail in a later chapter. Next semester, you'll be begging me to stop talking about acids. But for now, acids release H+ in a water solution. We'll go there and we'll extend that definition later, but for now, that'll work. Okay? So, how do I name acids anyway? Because this is something you'll have to do in the lab. Well, if it's the monatomic anion there, usually it's hydro, first part of the name, and then put an ic acid on the end of it. Okay? If it's a polyatomic ion, then you don't put the hydro on there. If it's the 8 ion, then it's an ic acid. If it's the ot polyatomic ion, then it's the us acid. All right? So for example, here's HI. HI is hydroiodic acid. Okay, always look for the H. That's how you know that it's an acid. Okay, hydroiodic acid. Okay, H2SO4. Well, polyatomic ion here, sulfate's -2. So you have 2 little +1s here to balance the whole thing out. So 2 of those little H's there. So what would I name this? Well, this is the 8, so this is sulfuric acid. Okay, here's HNO2. What's an NO2 minus polyatomic ion? Well, that's a nitrite. Remember, nitrate's NO3 minus. So NO2 minus 1 is a nitrite. So that follows this. So this is nitrous acid. What would HNO3 be? Well, it'd be nitric acid. So that's how you tell the difference. Notice no hydro because these are polyatomic ions. What about HClO? Well, remember this ClO is what? It's a hypochlorite polyatomic ion. So this is hypochlorous acid. Hypochlorous acid. And that's how you name acids. Make sense? Hydro if it's a monatomic, no hydro if it's polyatomic ions. Follow that pattern, you should be okay. All right? Last thing I want to say here is let's talk about your common acids here, because this is going to come up in a later chapter, and you're going to have to know these anyway, so I guess we might as well get a head start on it. When you see these 6 acids, these are your 6 common strong acids, and we'll talk about what strong means at a later time. But when you see these 6 acids, you need to recognize them on sight as acids, and you need to know what they are. Okay? So if you see HCl, that's hydrochloric acid. If you see HBr, that's hydrobromic acid. And if you see HI, that's hydroiodic acid. ClBrI. They're all in the periodic table. See, it's those three halogens. They're all sitting next to each other, right? One below the other, so that's easy to see. All right. The other three you need to know are hydrogen with a nitrate, polyatomic ion, HNO3, that's nitric acid. See, no hydro. H2SO4, which we talked about earlier, and that's sulfuric acid. All right, HClO4, a ClO4 minus is a perchlorate polyatomic ion. So if it's an 8, remember we use ic. This is a per8, so this is a perchloric acid, and that's HClO4. HCl, HBr, HI, HNO3, H2SO4, HClO4. These are your 6 what we call common strong acids, and that term will make more sense to you later on down the road. You need to be able to commit those to memory. You might as well memorize it now because it's going to happen. Trust me, you got to know it anyway, so you might as well just get it over with. Get that in your head. Okay? Recognize those, especially those on site, as acids, name, formula. Questions? I guess you'll have to email me because I can't hear them anyway. All right? And that's how you name compounds. All right? This little video here should be really important. I would certainly watch this again before you do the naming compounds lab, because this will help you name those compounds. So you'll get some extra practice on this, trust me, in lab. And that also happens to be the end of chapter 2. So we're finally done with chapter 2. It took us 45 to 50 minutes to get there, but we did it. So I guess in the next video, I guess we'll start chapter 3, and we'll move on from there. So I guess have a great day, and if you want to start chapter 3, you can. If you want to take a break and go get you some food or something, or rest your brain for a night, I understand. If you're watching this the night before the test, then you shouldn't be watching this the night before the test. You should have watched it a long time ago. But I guess you're going to do what you're going to do, right? Can't stop you. All right. But yeah, we'll start chapter 3 next time, and more fun stuff. So for now,